Happy Monday. We ate already. So I guess I should get Memorial Day on people's radar is a week from today. There won't be any class.
Yeah,
So no class next Monday.
all right.
But in the meantime, we're going to be going over the last little bit of content in here. And that's going to involve flow networks today, and then we're going to be talking about NP completeness later this week, leading into hopefully some approximation algorithms. We'll see how much time I have for all of that between today and the end of week 9, because I want to spend week 10 talking about interviewing. For assignments, we have our existing graph assignment, and I'll be adding the algorithms portion to that in the reasonably near future, with the idea that I want to, with the remaining time that we have, I want to get the current graph assignment in, I want to get an algorithmic version of that in, and I want some practice with NP completeness reductions in there as well. I can try to make that one a smaller assignment, but it will, at least with the current schedule, have to be on top of something else. It's not ideal, but it's some practice that we need given how difficult that material can be.
Oracle.com. That is not a site I've seen it at all.
It's gonna do the API, yeah.
So week 10 is only gonna be interviewing?
That's the plan for in class. There may be some extra, at least as far as content that is covered. We'll be preparing for the last exam that Friday as well during that week. But kind of the Monday and Tuesday of that week at the very least, I want to be spending.
Okay. Roll it.
I'm passing off exams to the grader today, so that hopefully those are turned around by the end of the week. What else? I think that's just about everything. Any questions before we dive into a little bit more background on this assignment? Okay. So I received a couple of requests over the weekend to talk about hash maps a little bit deeper. And so I think that's a very reasonable thing to do, given I've started to hear that people don't have a ton of experience with a hash map. So I want to talk about what a map is, and then how a hash map implements the map interface. So has anyone used a map before in any class? A few people used a map before? Maybe.
It's been a while.
So we're looking at key value pairs. The hash map takes those two parameters, the keys and the values. So we need to know exactly what the keys and the values are. The keys are always a set. Let's see where I can find that. Anyway, it's going to be a set object that you pass to your keys. And this makes sense. This is the same thing as a dictionary in Python, if any of you have been through and taken a Python course. But exactly as the dictionary works, you start with a bunch of words that are that's how you look up a particular definition. You don't want to look up a word, you want to look up a particular definition of a word. But the way that you access that in a dictionary is to look at the word itself. If it is a definition of the word snake, then you're going to look it up by the word and then find the appropriate definition in a list of definitions. So the keys are the set. It's the equivalent of the English word snake that has some different definitions. There's the animal, there's the, what do I want to call it? A personality trait. There's the item you use to unclog your toilet or your sink. There are a bunch of different definitions for the word. So if you're looking for a definition for any of those, you use the same key to look up the word. Then the value is going to be a list of potential hits for that set item. So all of the definitions of that word. So the values are in a list of some kind. So we have a mapping of keys to values, of words to definitions, of anything that is supposed to be some kind of lookup and storage for that lookup. That is always going to be what a map does. And a map can be implemented in a few different ways, one of which uses an underlying hash table, one of which uses an underlying tree. So there are two different classes that we typically use in Java for maps. We have the hash map and we have the tree map. And they have some pros and cons to using them, but I've decided on just hard code using a hash map for this because there's no reason to actually choose. So what is this hash map and how does it actually work underneath the hood? Actually, I'm going to give myself a little bit of board space. So if we recall what a hash table does, it's going to hash the key that we use to access the object. And then there also needs to be some kind of collision detection or collision resolution when we have hashes that map to the same area in memory, because the entire idea of a hash table is that we are taking a very broad spectrum of keys and we are mapping them onto a smaller list that fits more easily in memory. If we wanted to store an entire dictionary and we knew that the lookups were only going to be of a few words in that dictionary, we would want to map on just the ones that we want into our storage structure, not the entirety of the dictionary. So we're going to declare some amount of storage. Usually we vision this as an array of some kind. And that array is the size of our storage that we dedicate to it. But we want to store some number of objects in this hash table. We have a couple ways of handling that collision. We could either store something that collides in the next element, or it could be the head of a linked list, and we store every element of that maps to that index into that head of that linked list. And that's how the hash map is working underneath the hood. So I'm not going to worry about linear probing for collision detection, as you might have seen in the data structures class. These are all the heads to linked lists. So we have a very broad space of keys, and we want to create some kind of mapping from, big smiley face, our keys to our storage via some kind of hashing. So in this case, what we're storing is vertices and their associated values. So let's look back at the assignment structure for just a second and see if we can come up with what these hash maps are storing with regards to their keys and their values, and map it onto this idea. Okay, so when we see in here, we have our adjacency matrix and our adjacency list. Our adjacency matrix is just a hash map, whereas our adjacency list is a hash map inside of a hash map. So let's see if we can draw these out and visualize exactly what they are doing. So can anyone think about and tell me what this hash map string int key map is doing here? What does that mean?
Turning the string into it.
Yeah, so we're storing some string and we're mapping it to an integer. What is the purpose of this string in this int? That is exactly the right idea.
For the most part, but
Yeah, because what we have when we have an adjacency matrix is we have a 2x2, not 2x2, two-dimensional table. And we had rows and columns representing all the vertices. We had kind of our from vertex and our to vertex by rows and columns. But these are going to be indexed 0, 1, 2, 3, 4, etc. These are going to be indexed 0, 1, 2, 3, 4, etc. I read a file that contains a graph, and I see something along the lines of, we have vertex E. What index is vertex E in our table? We could do some kind of calculation and assume that the graph names start with A, and this is A is 0, B is 1, C is 2, D is 3, E is 4, and I should look it up that way. But that's making some assumptions about the underlying structure of the file and the vertices. What if we're loading in something completely different? A graph that where the vertices are named something completely different. Maybe they're names. Maybe there's something to the name of that vertex that is not an uppercase letter.
Doesn't it matter on like how high the hash key goes? It's only 10, then all 26 letters of the thing.
Yeah. If we had 26 vertices, then we'd have to shove them into however much storage space we have for that. Yeah. So there'd be some hash that does that. So instead of having to manually search through, is this the right vertex? Is this the right vertex? Is this the right vertex? We're going to hash the name of the vertex. And that's going to tell us what position to go find it. And that position will be the head of a linked list. So we still have to iterate the linked list to find what we're looking for, but at least there it tells us where to go find that vertex. So the time-saving metric. So that's what this hash map represents. Anyone have any questions on that? Visualizing the adjacency matrix as a key value pair. The key is the name of the vertex. The value is the index in the table to go find it.
At least I think I understand enough. Anyone else? Do they want to share their thoughts? I have a feeling we may be surprised again, but I think we get the idea.
So the adjacency list now is a hash map inside of a hash map. So a two-dimensional hash map. We have a key, and the value in the outer hash map is a hash map. It's telling us which hash map to go look at. Once we find that hash map, we need a key value pair that is a string to a double. How does that work with the concept of an adjacency list? Remember that an adjacency list is, instead of having a row column pair, now there is the head of a linked list to go iterate, to go find all of the connections for this particular source vertex. So in the adjacency matrix, the row and the column of the table were exactly the same. If we had a particular query, there's going to be a from and a to, and that combination will tell us what row column pair to go look at in the table. But with an adjacency list, now we need to go figure out every element of that. We need an internal representation that stores all of the source destination edges. It still needs to be accessed by name. So if there was a vertex named E, we need to go find the appropriate head of a linked list in order to iterate that linked list. But that head of that linked list might be in a linked list of possible vertices stored in an outer hash map. Let's see if we can draw this in a way that makes sense. We want to start horizontally or vertically? It's always the question with these. So we're going to start with some hash. We're going to take a string, the name of some vertex, whatever that is. We're going to hash that. And that's going to tell us where in this list of linked lists we are. So maybe that is here. That is going to give us another list that we need to iterate down, where each one of these is the head of a linked list. This stores the connections of that vertex. So this is going to be the names of a bunch of different vertices, of which V is going to be one of them. stored at that index. So we're going to iterate this linked list once this hash tells us that linked list. That's going to tell us we need to hash to get an element of the vertex here that is going to be this hash. So this is itself its own hash. So when we hash to here, this is going to also hash to give us the structure, the index that we need to look at here, that's going to contain all of the connections to the V vertex. So hash map inside of a hash map. Here we have the string that is the input. The keys are all heads of linked lists. That's what the hash map is telling us. Each one of these is its own separate hash map. And then from within this hash map, we use the key value pair to go from key to value. Sorry, this hash should be not here, but here. Right here. But the idea is we have a number of node names here that all map to or hash to this index. When we find the appropriate one here, stored in this are all of its connections. So this is source V destination something edge weight. Does that make sense? A little bit less so.
Okay, okay.
Yeah.
Actually, oh,
So we have this string being the name of the vertex. The name of the vertex leads to a hash map where we take that string when we find it, and that's going to give us a list of edge weights to other connected nodes.
okay. This is going to get. Oh,
So let's take a look at what the hash map can actually do in order to do this. What actual methods exist here? So if you know what you're doing with regards to hash tables, if we recall from data structures, there was the concept of a load factor. Does anyone remember what that load factor was or represented? That's how full the hash table needs to be before we resize, because eventually this hash table becomes so full that it's not really saving us a lot of time anymore. The goal of a hash map, if we read the very top of this, says, where do we talk about time complexity? Above this? No, there's nothing above this. We want, in general, constant time gets and puts. Yeah, here we go. Constant time performance for get and put. So this becomes violated as the hash map gets fuller and fuller. There are only so many bins, and each of those bins starts having enough objects in it where it's starting to approach linear time as opposed to constant time access. So if we have a number of bins that's proportional to the amount of data, then it's just a constant time lookup. But if we start having a number of bins that are proportional, let's say we have 10 bins and 20 pieces of data, then there is 2 pieces of data in each bin. It's going to take us time 2 on average to go find something. That's constant. But if we start having 10 bins and 100 items, now each bin has 10 items, and it's going to take us 1/10 of the time of iterating everything in order to find what we're looking for in the hash table. So it's closer to linear. It starts to become proportional to the amount of data that's proportional as instead of the constant time. So as that happens, we find ourselves needing to resize, make ourselves a bigger array, more bins to store things in. As we do that, it becomes a complicated and expensive process of rehashing every single element that was already in the table into a larger table. So this takes, instead of constant time for a single put, it takes linear time to put everything in a new list. So we want to minimize how frequently we are resizing this, but at the same time, make sure that it's big enough to hold all of our data and not so big that we're wasting a bunch of memory to store just a few things. There's a delicate balance there. So the load factor tells us how full the hash map needs to be in order to trigger that resize. So if we say 0.75, which I think it suggests, it's what's the default here. It says that it needs to be 75% full. There needs to be 75% as many objects as there are space for objects, and that will trigger a resize. Luckily, this is an implementation detail that you don't really need to worry about when you're using the structure. You just need to allocate a default one and run. So you don't really need to throw in an initial capacity and a load factor. It's good enough to just use the default constructor. For the default initial capacity and a default load factor, that is just fine. If you want to override the default initial capacity because there's going to be more than 16 vertices or 75% of 16 vertices, 12 vertices, then you could set a larger initial capacity to prevent having to go through that resizing just because you know. So an example from our lab, you could take a pass through the graph file and figure out how many vertices are there in this graph. And then you could create your hash map with an initial capacity of 75% of that. And that way you would know that there is going to be no resizing happening at all, unless the user adds additional vertices to the graph. Let's talk about what a hash map can do. Some of these are important, some of them are not as important. So clear, fine, just removes everything. An important one is contains key. This is going to take one of the keys, the set of keys, using our dictionary example, this is a word, and it will tell you if there is that word in the structure. It's a constant time operation. We just hash this key and determine, does that key exist in the hash table? If it does, return true, otherwise return false. So returns a Boolean, but just tells you whether or not an element of that set exists within the structure. Contains value does exactly the same thing with a particular value. So you pass in a particular, in the dictionary idea, a definition, and it tells you whether there is some word with exactly that definition. We can then look for what else is useful. Get. When we pass a key, it returns the value. If the value is itself a hash map, it will return that object. If the value is a list, it will return that list. If the value is an edge weight, it will return that edge weight. So get is a way of querying for values. And it returns all of the values associated with a particular key that is the parameter. Questions on any of these so far? Is empty just tells you whether there is a single thing, at least one thing in the hash map. It's true if it's empty, it's false if it contains at least one element. Key set returns just the set, the object of the keys. And then you can do things like merge, but that's more complicated than we need here. Put adds an element to the hash table. So we pass in a key and a value. It's going to hash the key to find the appropriate place. Check whether that key already exists. If so, it'll add the value. If not, it'll add the value to the key itself. Remove takes a key and removes it as well. So removes the values for a particular key. And we can query the size. We can query all of the values. So it's very useful for anything that has a mapping, which is why it's called a map. But again, I like thinking about it from the concept of Python's dictionary of, it's a nice visual for what this actually does. Questions or clarifications on anything relating to a hash table? Using a hash map to implement a hash table?
Who's using the built-in one?
Yeah, you're not making your own. You can just
Yeah.
plug and play an existing hash map.
Or just like import it into your
Yeah.
class, pretty much. Yeah,
Yeah.
I'm still like kind of adjusting that. I literally just spent like 15 minutes setting up all the classes. Asked us to try setting up.
Yeah.
You trying to think of the words here, and I had it imported when I was setting up the variable.
If you're using, do not implement your own version of this. That's way more effort than it's worth to do this. But yeah, you'll just need to import it and use it.
My question was, how do we iterate over a nested hash?
Yeah, that is a good question. So if you're going to the outer hash map, if you want to say something like, you can use contains. So contains value will ask if there is a hash map that is the value of a particular query. So let's again think of this in terms of the assignment where we take a string that is the name, and it's going to lead us to a hash map that's going to be the name and the weight pairs for everything that it's connected to. So B, the vertex B is connected to vertex U with weight 16. So this would be B maps to everything that it maps to. It maps to U with weight 16. It maps to, so you can see that this is an entire hash map. It's also connected to E with weight 6. It's also connected to, etc. So if we wanted to query something like, is B connected to E in some capacity? Or what is the weight of an existing edge between B and E? We know the B, so we can directly access B. So we can hash map, say, contains value. We're going to pass in the B and ask, is that value? You're going to make a query for the E and the 6 for that hash map. So does it contain a hash map of E to 6? If yes, then it returns yes. If no, then it doesn't.
Good to know. Actually, one more thing I should mention about the adjacency matrix variables above. When we put in private hash map string into it, I just found out that IntelliJ or Java does not like that, so I just typed in integer with capital I.
Yes, yeah, that is true. You can't actually have a primitive inside of a hash map. So this does actually need to be a capital I integer. This does need to be a class.
Hey, I'm just glad I'm helping out, letting everybody know.
That's good.
One has to at least. One has to.
Questions on that? So think of it just like a 2D array. In the same way, if you've used an array list inside of an array list or an array inside of an array, how do you access the row and then access the column? Each one is a different call. ArrayList.get, in this case, gives you a row, and then .get again gives you a value in a column. So one way to think of this in a nested form, have people done array lists inside of array lists in any capacity?
Not for a while.
So it's
Yeah,
been a while.
Yeah, most likely it's been. Yeah, it
Yeah.
feels faintly familiar in a way
I
that,
feel like since 211, because after you learn Linkless in 211, that's what they mainly focus on.
Yeah, I'm creating a little dummy idea here. This isn't actually stored, but it helps to envision that it is.
yeah, I think, he's right, I remember 211 and the last time we went through, something like that. And
So an array list dot get will return to you one of these lists. It doesn't return an index, it returns a list object. So this would be an array list of array list. It's a list of lists. So if you want to say, I want to access the 0, 1, 2, I want to access list 2 and element 3, 0, 1, 2, 3, I want to access row 2, column 3, you would get this entire list with dot get 2 that returns this entire list, and then dot get 3 says return me the third element of the list at position 2 of this list of lists. So it's the exact same with a hash map of hash maps, where we need to say, get the key of, using the key of the first, get the value that's an entire hash map. From there, you can use everything from a hash map to query anything about the keys or the values, because these aren't just single numbers, these are now all heads of linked lists with their own values. So I don't know, I can help people imagine this or draw this out in a more visual way during office hours, probably. But it helps to draw out and think of it like a two-dimensional structure like this, where the underlying structure is the structure you understand, and then the outer layer to that is also the structure you understand. Just stop thinking about the fact that the inner structure is itself, and instead think of it as, I'm just getting an element of a list. Right, when I get the element of a list, it itself is a list that needs an element.
Like an array list, you can get it constant time.
Yeah. It's not too much more complicated than thinking of a list of lists. Yeah, lots of stuff we can do. Any last questions about hash maps?
I have a question, not regarding hash maps, but about a link, but never mind, apparently it's a weird thing where Microsoft Edge can't access the site, but Google can.
I would not use Edge for anything.
I use it for opening PDFs.
I use it for downloading another browser when it's the only browser on your machine.
The only reason I use it is because of the Microsoft rewards, and I get like gift cards for Xbox. That's about it.
really, that's actually pretty crazy. Oh, okay. So what?
All right.
Maximum flow.
We have a little bit of time, and we're going to start talking about our next unit. There will not be any assignment based on this unit, but it may show up in a trace, kind of like Dijkstra's on a future exam.
Oh boy.
I would love to assign something with flow, but we don't really have time left in the quarter, and I think we have more important fish to fry with regards to implementation. That said, it's a very interesting chapter that really brings together a lot of what we've been thinking about with regards to algorithms. So I like this as a unit. So we've seen that graphs can model all sorts of things. We've seen it model things like distances between locations. We've seen it model social networks. We've seen it model digital networks and connections between machines. But one very interesting application of graphs involves where we have a material flow from a source to a sink. A source is where that material is created, and the sink is where that material is consumed. This could be liquid in terms of something like a river getting material at the source, glaciers, and sinks as they flow into the ocean. But it can also be things like shipping routes, where we have a warehouse that produces something and a retail location that sells something. And we want to make sure that there is equivalence between how much of the material we make and how much of it we sell. We don't want it accumulating in certain places. Data pipelines, from things like a database to a query device over a network. Liquid flowing through pipes. Current through an electrical network. Parts working their way through an assembly line. There are tons of different kinds of source to sink relations in the real world, and being able to model that digitally is incredibly useful. So to do this, we're going to use directed graphs, as we've seen before, and just the edge weight is going to be the amount of material flowing from source. I guess it's not necessarily a sink, it's from the source to the destination between that edge that may or may not be the actual source or the sink for the material as a whole. The edge weight for this is not the amount of material that is currently flowing, it's the capacity for flow in the network. So let's give you an example of this. We want to figure out how much can be passed through the entire network from source to sink. That tells us how much to produce at the source and what is the rate at which we can sell and resupply at the sink. So we start with some assumptions. This is a very important assumption that we will talk about in more detail in a little bit. If there is a directed edge from U to V, there cannot be a reverse edge from V to U. That means that even though this is a directed graph, we can't have two edges in alternate directions, going between the same two vertices. We also can't have self loops. We can't ship something from the source back to the source. It kind of seems like a waste of time anyway. Does anyone send mail to yourself, except not you at a different location, you at the same location? Like, here, take this letter, store it for me, and give it back to me in 2 days.
Really early refunds where it just came out of the place.
So we need to identify the source vertex and the sink vertex. That's an important part of this problem. We need to know where the material is being created and where it is able to leave the network. Once we sink the material, then it's gone. It's like selling it at a retail warehouse. The example we're going to use is a hockey puck shipping company. The source is going to be Vancouver, BC, and the sink is in Winnipeg, Manitoba. We can ship on a daily basis 16 tons of pucks from Vancouver to Edmonton, I'm going to go with tons. Tons of pucks from Vancouver to Calgary, 4 tons of pucks from Calgary to Edmonton, 12 from Edmonton to Saskatoon, 9 from Saskatoon to Calgary, 14 from Calgary to Regina, 20 from Saskatoon to Winnipeg, and 4 from Regina to Winnipeg. So the question is, how much can we make in Vancouver on a daily basis that can also arrive in Winnipeg on that same daily basis? If you have more pucks produced in Vancouver than we have reaching Winnipeg, then at some city in between them, they're just getting a larger and larger pile of pucks over time. And that's no good. I know Canadians love hockey, but probably not enough to have tons and tons of hockey pucks sitting in a warehouse in one city. If there's ever fewer than that, then that means that we could produce more and ship more, hopefully to make a higher profit. Further constraints, there's a capacity constraint, which we just talked about. We need the flow to be non-negative. It doesn't make sense for there to be a negative flow. It might make you think that's, okay, well, that's flow in the opposite direction, but we would need a separate edge to represent that, so we don't allow any of these edges to ever be negative and should not ever exceed the given capacity. So if there is 12 tons being shipped between Edmonton and Saskatoon, that is the limit. We cannot ship more than that. We can't hire people to walk single pucks between them. We can only put them on trucks. There's the concept of flow conservation. This means that at every single middle point, whatever is coming in must also be shipped out on that same daily basis so that we don't get puck accumulation at any particular point. If we have flow in greater than flow out, material starts to, I guess I can use the word aggregate, but you start drowning in pucks. If flow out is greater than flow in, we don't have the supply to meet the demand. We can't fill the truck that is leaving. And that's not necessarily good if we could have more there. That's saying that we were paying for extra space. So, goal of the puck problem is figure out the largest number of tons of pucks that we can produce in Vancouver, deliver to Winnipeg, regardless of the actual route that is taken. We're not worrying about efficiency here. We're just trying to maximize the number of pucks that we can make and get to Winnipeg in a given day. We're renting these shipping routes. We can't make our own. There's an existing trucking company that we are leasing trucks from. We cannot have them changing their routes. We knew from the prior slide that for each middle city, intermediary city, flow in has to be equal to flow out so that we don't accumulate pucks in these middle cities. And if we could have flow in both directions, then it violates our constraint and we just don't allow it. And we'll talk about how to handle that later on. It can be solved, but we want to introduce the problem a little bit more to do that. But we're going to basically, here's how you, okay, I'll just tell you how you handle it. Here is the concept of between V1 and V2, we have 10 tons that can go from V1 to V2, and we have 4 tons that can go from V2 to V1. We just are, to be able to model this, going to create an extra vertex in between them and model one of the edges as flow to that intermediary vertex.
Yeah.
And that completely solves the problem. You just create a ghost town and you ship one of them to the ghost town and out of the ghost town, and it's the exact equivalent. Maybe it's a future city. Maybe it just hasn't been founded yet. We're ahead of the plan here. But now there are no anti-parallel edges anymore. We don't have 10 in one direction and 4 in the other direction between the same vertices. We just had to make a ghost town.
Okay.
Any questions on any of the setups so far?
I can't tell you honestly, but I have a feeling there's more to this than I think I know right now. Well,
Doesn't that mean we are altering the routes? We're not, because we're not actually shipping them to a place called V prime. We're shipping directly from V1 to V2, but in the graph, we're adding an extra node that says that as we ship from V1 to V2 in the log, it says it's going through V prime. And we're doing that just so that we can model these anti-parallel edges. And we need to be able to do that sometimes. Any thoughts on solving the problem? If just looking at this graph, if I asked you what is the maximum flow between S and T, how would you intuitively solve the problem?
I'd start at T and start working backwards, look at how much can get to T, and then look at if there's any way to get the maximum of both of those that are getting to T,
Okay,
so on and so forth until you make it back.
yes. There's no other way to get to T other than the direct incoming edges to T, so it looks like 20 plus 4 is the absolute maximum that we could ever hope is getting to our sink. The question is, how much of that 24 can we get? Any other thoughts?
Much of it. Good question. One idea though.
It's like the dice, but like you start where you wanna end. Start at T.
Yeah, we need some path. We need some simple path from S to T. We need some way to get there. What happens when you start to consider a particular path? Like, let's say we find the S to V1 to V3 to T route. How much can flow between S and V1 and V3 and T? Well,
Yeah, that's the,
yeah, so we can basically just remove this edge. Subtract 12 from each of these edges. That's a 4, not a Y.
okay,
And this edge no longer exists, but we could add 12 to the cumulative flow between S and T from that route. Yeah,
It's the idea to look at the smallest edge number along a route and then look at the like loss depending on each route. So you choose the route that has the least amount of loss for getting to the destination.
interesting. What do we mean by loss here?
For instance, there the maximum flow that would be 12, since that's the smallest number that you can.
Yeah, so the
So
B's
you
would be the
have
loss, the
remaining
4 and the 8.
Yes, you have, so you have the remaining 4, you can't transport that, it's the max between the, there is 12. And then you have the 8 after, which is lost because you could only transfer 12 to that 20.
Sure. Is it guaranteed to be loss? Because we could ship this 4 here, carry that 4 all the way down to V2 via B prime, and then over to B4, and then up to T. And we have a way of reusing that 4. We'd just be saying that the 16 that ships between S and V1, 12 of it should be siphoned off to be shipped to V3, and 4 of it should be siphoned off to ship to V2 via this pseudo V prime.
oh, okay, yeah, I see it.
So thinking of it as loss might be a kind of a one-step loss. But if we iterate this process over and over and keep looking for simple paths that exist between S and T, if we have a way of modifying this graph to show and account for routes that we've found so far, the idea is that this would eventually iterate and converge on the actual answer. The question is it any more complicated than that? Would that process completely solve the problem? The answer is it completely solves the problem. With one small caveat that I will get to in a second, which is an efficiency caveat.
That sounds like a lies benefit doesn't completely solve the problem.
There are certainly some assumptions that we can make to set up a network that does not converge quickly. So that's what we're gonna come back to and talk about tomorrow, I think, rather than getting into the next thing with under 1 minute to go. I think we'll stop here and we will reconvene tomorrow to talk about the rest of this. It is a very interesting problem, but one that maps onto a lot of other problems. I have office hours starting now. If we'd like some assistance getting started on the existing assignments, or getting unstuck if you have gotten the chance to get started and are stuck. And you'll see you for that, or I'll see you tomorrow.
Okay.